Welcome to week 7. We're going to start 9.2. This one is called Exponential Decay. Last week we actually we talked about exponential functions, and then we specifically talked about exponential growth. Now we're actually going to look at what is the difference between having exponential growth, which was last week, and then we're going to do decay today. One of the big words that comes up quite often with exponential decay is something called depreciation. You probably have heard this word before. A lot of items that you buy depreciate over time. So that's when something that actually loses its value over time. And whenever you do this, we're always going to subtract the number they give us from 100%. So it'll give us a depreciation of a certain percentage, and we subtract that from 100% to see how much value it's actually holding over time. And you'll see how that works when we go through a problem. Example 1. Suppose a new SUV costs $36,025 and it depreciates 15% each year. We're going to write an equation that gives the SUV's value when it is t years old. So we're going to use t as our variable. We're going to say it's f of t. I don't know if you remember this, but we did the formula for exponential functions was f of x equals a times b to the x. So I'm using basically this formula. A was the starting value, b is your growth factor, how much is growing, and then your variable is always in the exponent here. We're just going to use t for the x, the variable, instead of using x. So f of t, because you said to use t for years old, equals, well, what is the starting value? A, that is $36,000. So it's $36,025 times, I'll put this in parentheses, our b value is our growth factor. So if it depreciates 15% per year, this is what I was saying, you always have to subtract that number from 100%. So we're going to go off to the side here, and we're going to take 100% minus 15%. So how much value is it actually holding every single year? That would be 85%. So we're not going to put 85% in as our number. We're going to change that to a decimal. So remember, you got to move that over twice. So it's going to be 0.85. So 0.85. And that'll be raised to the t power, because that's your variable. So your starting point is $36,025. That's how much it costs to buy the car. And then the value it's actually holding is 85%, which also means it's depreciating 15 each year. So this is the formula we're going to use to answer the rest of the questions here. What is the value of the SUV at the end of the first year? So what are they asking us to do? Plug in 1 for t. So if t equals 1, we're going to plug that in up here and on the left as well. So we do f of 1 equals 36,025 times 0.85 to the first power. Now that one's actually pretty easy to evaluate because the exponent is only 1, so you don't even have to put it in there. We're just going to do 36,025 times 0.85. So pull up your calculator. 36,025 times 0.85. So after 1 year, it is now worth $30,621.25. $30,621.25. So you can see the value has gone down in the past year. So you can actually continue doing this. Now we can figure out what's the value of the SUV at the end of the second year. The only difference is we plug in t equals 2. So we're doing f of 2 equals 36,025 times 0.85 to the second power. So that one's going to take a little longer. Don't forget, you have to do exponents first before you multiply them together. So I'm going to do 0.85 to the power, this is the XY button. You can see a little caret up here as well. To the second power equals this decimal. Then we multiply that by 36,025. So now we've dropped all the way down to $26,000. 26,028.06. So within 2 years, we've dropped almost $10,000 on this SUV when you bought the car brand new. 2 years. So now if you were to turn around and sell it after 2 years, it's only worth $26,000. All right, so let's jump go a lot further ahead. Let's go from 2 years all the way to the 10th year. So what happens if we plug in 10? It's not going to be worth that much, right? So let's do the setup. That's going to be f of 10 equals 36,025 times 0.85 to the 10th power. So I'll run you through that one. You got to do the exponent first. So we're going to do 0.85 to the 10th power. It's a pretty small decimal. Times the 36,025. So it's going to be worth a little over $7,000. $7,092.4. So after having the vehicle for 10 years, it'll be worth around $7,000. It lost almost $30,000 worth of its value. Party, what do you think the graph will look like? So last week we had graphs that looked like this. If you remember, they started out really slow and pretty low, and then it rose really fast. So it was kind of slow, and then it went up really fast like this. The question is, what do you think this graph is going to look like? Now we're starting at a pretty high value. So think about, we started at $36,000 at the very beginning. So that's kind of our starting point. And then over time, as you go across the x-axis, we're going to decrease our value here. So we're starting at a very high value. So it's like 36,000. And then over time, as we go across the x-axis, going that way, the value is drastically decreasing. So it's going to be going down and then to the right. So the question is, what kind of graph would that look like? Which we'll see one in a minute here. And the other question is, will this graph ever cross the x-axis? So think about that. If we're decreasing the value, so say this is value, if we decrease that over time, this is time, will it ever come down and touch? And what would that mean? Well, that would mean that the value, if it's all the way down here, is at 0. So will the car ever be worth $0? In real life, probably not. And also, graphically, when we do exponential decay, will this graph ever cross the x-axis just like last week? No. There's actually going to be an asymptote there, just like there was last week. All right, the formal definition of exponential decay. As the x values, so as x increases, this would be like increasing time on the car one. As we increase time of owning the vehicle, what happens to the y values? This would be your value of the car. The value of the car decreases. So with decay, if we increase the values on the x-axis, the y values decrease. So specifically, we have this formula, f of x equals a times b to the x. So this is for all exponential functions. The only restriction we have here to make it a decay rather than a growth is that the b value, so this value right here, this b value, has to be between 0 and 1. So the way I would write that is b has to be less than 1, the number 1, but it has to be bigger than 0. So this is kind of smashed right in between the number 0 and 1. It can't be equal to 0. It can't be equal to 1. It has to basically be a decimal or a fraction between 0 and 1. And then the last restriction is a is greater than 0, which is obvious because you can't have a 0 in here. That would make the whole thing 0. So we saw last week that the b value for growth had to be greater than 1. Decay means it has to be between 0 and 1. We're not talking about any negative numbers in the B value yet. Example 2. Suppose the value of your car is now worth $5,780.54. So this is the current value, right? It's now worth that much. When you bought the car, it was actually worth $14,675. If it is depreciating at 17% each year, how many years ago did you buy the car? This is kind of like a guess and check. We're going to set up the equation, and then I'm going to show you by plugging in some values and see. We're going to guess how many years it took to get down to this value. So the setup is a little different because they gave us our current value, and we know our starting point and we know our depreciation. What we don't know is our years, how many years ago. So I'm going to use T for years, and that's something that we don't know. So if we were to set up the equation, we would say f of t equals your starting point, which is the 14,675, times depreciating at 17%. We don't put 17 in there. We don't put 0.17. We have to go off this side and do 100% minus 17, which is 83%. We'll change it to a decimal, so 0.83, and then raise that to the t power. We don't know the years. The only other thing we know is how much it's currently worth, the 5,780. So where would that go? If we know how much it's currently worth and we're trying to figure out the number of years, that would go on the left-hand side. So we're going to replace f of t with that number. So let's just do that. Let's just erase it. And we want that to be equal to the 5,780.54. So here's the question. What number goes in for t so that it equals that amount? So it's kind of just like a guess and check. How many years do you think it would take to go from 14,000 to 5,000? So let me go ahead and try one. I think I know the right number to put in. I'm going to guess 5 years and see how that works. So if I were to plug in 5 for t, it would look like this. 0.83 to the 5th power, because I'm guessing 5 years. And if I multiply that by 14,675, there, I get the number. 5,780, 5,780. So it took 5 years. Again, you'd have to guess and check. I kind of already knew the answer by looking at it. But if you tried like 4 years or 6 years, you'll get somewhere close to 5,780, but it won't be exact. Maybe it'll be $1,000 or $2,000 off. So the answer, I guess, would be it would take 5 years. Take 5 years. Again, it's kind of like a guess and check. Example 3. Suppose you buy a watch that costs $140, and this is going to depreciate 14% each year. Complete the table and show the graph of the value of the watch over time. First, we're going to write the equation for the value of the watch at t years, so he's still using t. So we're going to say it's f of t equals our starting amount, which is, you got to start with your starting amount, $140, times what number goes in here? Well, if it's depreciating 14%, we have to subtract that from 100, which would be 86 now. So 0.86 to the t power. So we're going to graph this. We're going to put it in a table and fill this stuff out, but I don't want to be plugging in 0 through 8 and getting all the values. So instead, I'm going to give you a website to use. It's called GeoGebra. It's a graphing calculator. I'm going to show you how to use that instead. So what we're going to do is I'm going to plug in, if I can see both things over here, I'm going to plug in the equation over here that we wrote out. Now, I'm not going to type in f of t, but it does recognize y. So I'm going to hit y equals 140. And then I'm going to put the parenthesis set, 0.86. Then I have to move my cursor over. It's inside the parentheses. I have to move it on the outside. And then raise that to the x power. So you have to hit shift and the caret button. It's number 6. Now it looks the same. Looks good. Once you have that in here, you'll be able to see the graph over to the right, which I'll show you in a second. But we can also click these three little buttons here and click on Table of Values. And when you do that, it will come up and say, well, what kind of table of values do you want? Where do you want your starting value? Starting value, if you look at our table, it starts at 0 years. So when we first bought the watch, it was worth $140. The end value we want would be 8. The step just means it's going to give you every integer between 0 and 8. So if you hit OK, here we can see it. 0, it's worth 140. At 1, it's worth 120, 40. So we can just copy these numbers over into this table, which I'm going to do. It's a little easier than putting it in every single time. At 1, it's 120.4. 2, it's 103.54. You don't have to be very specific because when we graph this, it's going to be a big estimate anyway. 3 is 89. 4 is 76.58. 5, 65.86. 6 is 56.64. 7 is 48.71. And 8 is now worth $41.90 if we round it up. So let's graph it over here. We have 0, 140. Let's put a dot here. 1 is 120. So pretty close to 120 exactly. So it's right here. 2 is 103, which would be a little bit above the 100 here. 389. Close to 90 here. 4 is 76. There's 70 here, so like right here. 5 is 65, which would be right here. 6 is 56. So 6 is 56, so maybe this is 50 right here. 7 is 48 right here. And 8 is 41, so right about here. So you can kind of see this is kind of decreasing, not really fast, but faster than it is later. So at the beginning, it's kind of decreasing more quickly, and then it's starting to level off. So if I were to connect these, so you can see what they look like. If I were to connect these, it's kind of going down here, and then it's like leveling off a little bit here. Probably going to go like that a little bit. So you can't see it too well with my picture, although if you do go back to the GeoGebra graphing calculator, you can zoom in and zoom out by using the mouse. So if you use the mouse wheel and scroll out or down, you can see it much better at a bigger scale. So here it is, starts at 140, and then in this case, it's dropping pretty quickly. Our scale just went, by ones. This is going by tens here, but you can see it really dropping out and then coming down. So you can kind of zoom in and look at it. This is how you know it's exponential decay. It's dropping down over time. So I think that picture is a little better than the sketch we have here to show decay. All right, example 4. Suppose a new piano costs $8,500 and depreciates 6% each year. Write an equation that gives the piano's value when it is t years old. So we can quickly go through this. So we have f of t equals our starting value, which is 8,500. Oh, man. 8,500. And we're multiplying that by what? 6%. So it's only going down, if you subtract it from 100, is what? 94. So 0.94 to the t value. Again, I would not be interested in putting this in the calculator. You can put each one in the calculator to find 3 years and 6 years, but you could also go back and plug it in to this calculator here. So what we have, y equals, let me move that over so you can see. You can do 8,000. It's good to practice using this because it's easier, I think. Okay. 850, parentheses, 0.94, raise that to the x. And then once you do that, you can bring up your table. 3 years, so we're going to look at 3. It's worth 7,059. So we can actually say f of 3, and just put our answer here. 7,059.96. And then f of 6, just look at the value. At 6, it's 5,863. You'll know you did something wrong if you put the equation in and your values are going up instead of down. All right, we only have like 2 more examples to do. Graph the following equations on the same grid. So I'm going to do the same thing, but over here I'm just going to do a sketch. And we can just look at what it comes up with on the GeoGebra site by plugging in these equations. So let's go back and actually do that. I think you have to click on the calculator every time for it to come up. And we can delete this stuff. So the first one will be 3 to the x. So 3, and you have to do the shift 6 x. That'd be first one. Second one is y equals 1/3. I just had the division sign to get that 1/3 there, which is right next to the shift. It's a slash. Raised to the x as well. Okay, and then I'm going to bring up the table of values for each one. So table of values. The first one is 0, 1, 1, 3. Now the problem is we're starting at -2. So I'm wondering if I can change the table set. Edit. Settings. Well, I don't know exactly how to change the table set right now. Oh, maybe I can click edit on here. Okay, so if you're in the table, maybe click on these 3 dots and hit edit. Okay, starting value, we want to go to -2. That's better. And we're only going to end at 2, so we're not going to go that far. Okay, so here's our values. So 0.1111, well, where does that come from? I'll show you in a second. I'll put it in here, 0.1 repeating. We have 0.1 repeating, and then we have 0.3 repeating, and then 139. So 0.3 repeating, 139. So let me show you where the 0.1 comes from. If you plug in -2 into this equation, it's 3 to the -2nd power. If you remember how to deal with negative exponents, that means you have to make it over 1 and flip them around. So this is the same thing as saying 1/3 squared. And 1/3 squared is 1/9. And 1/9 happens to be 0.1. So that's how they get that. Okay, going back to the other one, hit calculator. I want to find look at the table on this one, the 1/3 to the x. So we'll do table of values. It's already set correctly, -2 to 2. Oh, now it's showing us both. Nice. We can see f of x and g of x here. So the second one is what we need over here, the new one. -2 is 9, 3, 1, 0.33, and 0.1. So it's kind of just the reverse. 9, 3, 1, 0.3 repeating, and 0.1 repeating. So if you look at these numbers here, y to the 3x, this is a number bigger than 1. So b is greater than 1. This is going to be a growth function. The 1/3 in here, this is between 0 and 1, because 1/3 is a decimal, 0.3 repeating. That's going to be decay. So here we're going to have growth, and here we'll have decay. And I'm just going to do a sketch of it based on the GeoGebra site. So if I already have it on here, I am zoomed out quite a bit. Maybe I should zoom in. So just go down here so I can zoom in a little bit. See it a little better. There we go. So the blue one here is the exponential growth one. That's a 3 to the x. And then the purple one is the decay, how it's going down. So look very similar. One's just growth, one's just decay. So I'm just going to do a basic sketch of that. Also, can we see where it goes through the y-axis? That's going to be important. It goes through right at 1. So they both touch the y-axis at 1. So we'll say it's right here. So the 1 is really close to the x-axis for a while and then jumps up like this. Okay, I'm not really good at drawing these sketches for sure. Goes down and then shoots up like this. The other one comes up from here and then goes down like this. There we go. Again, one's growth, one's decay. They look very similar. It just depends on whether it's increasing fast or if it's decreasing fast. Based on those two ones, the two we just did, now we're going to go through the domain, range, asymptote, and all those things. So this is all our growth ones. Again, these are growth because it's bigger than 1. So we did this last week. What's the domain? The domain was all real numbers. What is the range? The range was y is greater than 0. What is the asymptote? The asymptote is the line doesn't cross. That is the x-axis. This is all answers from last week because we did growth last week. What are the x and y intercepts? Well, the x-intercept, there isn't one because it doesn't touch the x-axis, so none. And then the y-intercept, we just talked about that on the graph. It crosses at 1. Maybe it'd be easier to see. If I could shrink this down, maybe. Maybe not. It crosses at 1. It is not going to touch the x-axis. It looks like it does, but you can keep zooming in. And it actually doesn't. You just have to keep zooming in, like really far. It keeps getting closer and closer, but never touches. It looks like it does when you zoom out, though. So that is with the one we just did with the blue one. It crossed at 1, never touches the x-axis. The domain goes on left and right forever. The range and then never goes below 0. The domain and range, all these answers over here for the purple graph I have up here is pretty much exactly the same. Domain, no different. All real numbers. So even though this is decay, the nice thing is we get very similar answers. Decay. Okay. What is the range? Same thing. Has to be bigger than 0. Asymptote, there still is one. It's the x-axis. Oh, I never answered the y-intercept. I'll go back in a second. What are the x and y-intercepts? The x-intercept, none. Y-intercept is 1. They both were 1. By looking at that, crosses at 1. Okay, last problem. Probably the easiest problem out of everything. Determine if the following are exponential decay or growth. Remember, decay has to be the b-value between 0 and 1. Growth, the b-value has to be bigger than 1. That's it. That's the only thing you're looking at. You're looking at specifically the b-value whenever you have f of x equals a times b to the x. There may or may not be parentheses. It doesn't matter. Whatever is connected to that x variable is what you're looking at to answer growth or decay. So f of x equals 2 times 2/5 x. So 2/5 is definitely a decimal. What is the decimal? It's 0.4. Is that between 0 and 1? Sure is. It's decay. B, f of x equals 4/3. That's also a fraction. But what kind of fraction is it? That is 1.3 repeating. You can just do 4 divided by 3. So 1.3 repeating, that's a number bigger than 1, so that's growth. C, 10 times 1.2. Well, we've already done one similar to that, 1.3 and 1.2. That's also bigger than 1, so it's growth. D, 3 times 0.89. Notice I'm not looking at these front numbers at all. Doesn't matter. This is your growth rate. 0.89 is between 0 and 1, so it's decay. And the last one, 0.3 is on the outside there to trick you, but we're looking at this number, 2. So B is bigger than 1. That is growth. Hopefully that wasn't too difficult. It was kind of long. Sorry for that. But there's, I guess, a lot to talk about between growth and decay. And again, if you get stuck with anything, go back and rewatch it. And hopefully this is good enough for you to complete the assignment for week 7. We'll see you next week.